In this section we'll just review a couple of important concepts which are related to address spaces. So when we think about the address space of a process, we have at least two different models that are available to us. One is an address space which is known as the logical address space, and then the other is known as the physical address space. So we need to have a separation between these two address spaces and have an understanding about not only the fact that they are separate address spaces, but also as well that they relate to each other by a process that we'll describe as mapping. So the two types of address space are logical address space and physical address space. So a logical address space belongs to a process and is internal to the process's view of itself. So this is a set of machine code instructions that reference addresses that are private to a particular process. Now these logical address spaces and logical addresses, they have to be converted into physical addresses, and those addresses are the actual physical addresses in main memory. So the user process sees logical addresses, and that is, if you like, its delusion, and the machinery of the computer, and in particular a special circuit which is known as the memory management unit, well, it is responsible for translating the logical addresses into physical addresses. So this is really an important distinction, because without this distinction then processes have to be hardwired to physical addresses, and that simply won't work for reasons that I think will become obvious after a while. Okay, so we make a distinction. We say for each process that exists, it has two address spaces. One is its logical or virtual address space, and that is private to the process. The size of this address space is very, very large. We don't need to worry about it for the moment, but it is very it's humongous, really. It typically is larger than the amount of physical memory that is actually installed in your typical computer. But in any case, this virtual address space is private to the process, and that then has to be mapped to the physical address space, which is the set of addresses which are actually being used by the process in main memory. And as I pointed out, this translation, this runtime mapping of logical addresses to physical addresses, well, that is carried out by a hardware device known as the memory management unit. The process, when it's executing, it simply doesn't see this memory management unit. It's completely opaque to it, doesn't even know that it exists. And in fact, the CPU as well, it doesn't see this. The CPU works with logical addresses. So in order to discuss this and get some insight, we're going to look at three schemes. The first is called simple relocation, the second is called multiple partition, and the third is called paging. So the first two are ancient and only used as examples. The third technique is used in contemporary systems, and that's realistic. Another thing that we'll keep in mind as well is this diagram here. We won't really discuss this in this particular lecture, but we'll certainly have a lot more to say about it in terms of virtual memory. So virtual memory is an elaboration of the memory processes, the memory mechanisms that we're describing just now, but this is the internal structure of a process. Okay, so the next section deals with memory management desirable goals. So obviously what we're looking for is memory management which first of all is safe. So in order to do that, we have a principle. One of the principles that we have is that processes should not be able to access the address space of another process or the kernel. And we also, as a kind of follow on from that, as a consequence of this idea of protection, we have another principle, which is the principle of isolation. So really this is going back to the theme that we've expressed at the beginning of nearly every lecture that we've done so far, which is that every process exists in its own safe private bubble. We also want efficiency. We want it to be fast. So when we're translating logical addresses into physical addresses, we want that done quickly. And also as well, although we wouldn't think about this in too much detail, we are mindful of the fact that RAM as a physical resource is potentially something that we can run out of. So that doesn't really happen when we think about tablets or phones so much, and even PCs. But if we're doing something more advanced, then we have to be aware that we can actually exhaust RAM. So one of the things that the system has to have is a fallback, a mechanism that can cope with the amount of physical RAM in the system being exhausted. And then our final consideration is really one of transparency. Everything that's done by the operating system to achieve this virtualization for each process should be completely invisible to that process. So we've talked, as I said, on many occasions about the delusional bubble that processes execute in. Well, the delusion that we want to create for the process in terms of its memory management is a very simple one. We want each process to believe that it has exclusive and absolute access and control over a really vast memory, and that there's no competition from any other process or from the kernel.